For decades, the United States Navy has held a near monopoly on the operation of supercarriers. Today, however, things are changing. We will comprehensively compare two of the most advanced aircraft carriers currently afloat. The American ship is the United States Navy Gerald R. Ford class. The Chinese challenger is the PLA Navy Type 003, named the Fujian. We will examine their design philosophies, their flight deck optimization, their catapult launch systems, their airwings, and their propulsion, among other variables. To understand the Ford, we must first look at its predecessor. For over 40 years, the backbone of American naval power has been the Nimitz-class supercarrier. The Nimitz class is widely considered one of the most successful classes of carriers ever constructed. However, by the late 1990s, the United States Navy realized that the Nimitz hull had reached its architectural limit. As new technologies, heavier aircraft, and advanced sensor suites were added to the Nimitz ships over their lifespans, the vessels had to add on more and more upgrades, and critically, their ability to generate electrical power was maxed out. Furthermore, the operational cost of maintaining a crew of nearly 5,000 sailors per ship was becoming financially burdensome. The Gerald R. Ford class was born from a requirement to move past these limitations. The US Navy introduced new and vastly more powerful A-1B nuclear reactors and integrated a massive amount of automation. This automation was critical, as it allowed the Navy to reduce the ship's crew size by 700 sailors, saving billions of dollars in personnel costs over the 50-year projected lifespan of the vessel. The Ford represents a ship built around its electrical grid, designed from the keel up to power the directed energy weapons, advanced radars, and the electromagnetic catapults of the 21st century. A key design goal for the Ford was to dramatically increase the sortie generation rate, which is the number of aircraft launches and recoveries a carrier can execute within a 24-hour period. To achieve this, engineers optimized the flight deck layout and the location of the island, while leveraging the benefits of the EMALS electromagnetic catapults. On the other side of the Pacific Ocean, the Fujian represents breathtaking improvements for the Chinese shipbuilding industry. To appreciate the Fujian, we must trace the brief history of China's carrier program. China began its carrier ambitions by acquiring an incomplete Soviet-era carrier, which they painstakingly studied, reverse-engineered, and rebuilt into their first aircraft carrier, the Liaoning. They then built a domestic copy with some improvements called the Shandong. Both the Liaoning and the Shandong are classified as short takeoff but arrested recovery vessels, commonly known by the acronym STOBAR. A STOBAR carrier utilizes a curved ramp at the bow, known as a ski jump, to loft aircraft into the air. While simpler to build and operate than catapults, the ski jump comes with severe technical penalties. Aircraft rolling up a ramp under its own engine power can only carry so much weight. Therefore, Chinese fighters launching from the Liaoning and Shandong must significantly reduce their fuel loads and weapons payloads just to get airborne. This limits their combat radius and strike capability. Crucially, a ski jump also prevents the launch of heavier, slower support aircraft, such as propeller-driven airborne early warning planes. The Type 003 Fujian fundamentally changes this paradigm. It abandons the ski jump entirely. The newly built Fujian is a catapult-assisted takeoff but arrested recovery vessel, known as STOBAR. By utilizing catapults to physically hurl aircraft off the deck, the Fujian allows Chinese fighters to launch at their maximum takeoff weight, fully loaded with missiles and fuel. It also allows the deployment of AWACS. the Fujian marks China's definitive entry into the privileged club of navies capable of operating full-sized, comprehensive carrier airwings, signaling a transition from a regional force to a true blue water navy built for power projection. Let us look at the exterior of these vessels and examine the nerve center, the island. The island is the tower structure that rises above the flight deck, housing the bridge, flight control, and primary radar systems. On the forward, the island is significantly smaller than the Nimitz class, and it is positioned nearly 40 meters further aft towards the stern. Because the forward is powered by nuclear reactors, it does not require exhaust funnels, routing smokes and hot gases from engineering spaces within the hull up through the island. Free from these massive exhaust pipes, naval architects could shrink the island and push it out of the way. Pushing the island aft creates a massive, continuous and unobstructed area of usable flight deck forward of the island. The US Navy refers to this expansive zone as the pit stop. The pit stop idea enhances flight deck efficiency. Aircraft landing on the forward can taxi into this large area, where they can be simultaneously fueled, armed with munitions from nearby weapons elevators, and serviced by deck crews without ever having to move near the island. This minimizes aircraft movements and reduces turnaround time, and is a key contributor to the forward's increased sortie generation. In sharp contrast, the Fujian features a noticeably larger island that is located much closer to the midsection of the ship. This layout is dictated by the Fujian's conventional propulsion. Because the Fujian burns marine fuels in steam boilers to generate power, it requires large smokestacks to safely vent the exhaust away from the flight deck and aircraft. These smokestacks must be routed through the island superstructure, necessitating a larger physical footprint. The midship placement of the island is less optimal than the forward. A large structure situated in the middle of the starboard side divides the flight deck into distinct forward and aft zones. This disrupts the smooth flow of aircraft taxiing along the deck. Deck crews on the Fujian must maneuver jets carefully around the island, a process that inherently slows down operations, increases the risk, and degrades overall flight operations efficiency compared to the expansive, unhindered pit stop model of the forward. Moving on from the deck layout, we must compare the aircraft elevators. Elevators are vital arteries of an aircraft carrier. They are responsible for moving aircraft and support equipment between the enclosed hangar bay below and the exposed flight deck above. The Gerald R forward is equipped with 3 aircraft elevators. 2 are located on the starboard side, forward of the island, and 1 is located on the port side, towards the rear. The Fujian is only equipped with 2 aircraft elevators. Both of the Fujian's elevators are located on the starboard side, with 1 positioned forward of the island and the other positioned aft. The forward's inclusion of a 3rd elevator provides a tangible advantage in both throughput and resilience. A 3rd elevator means the American carrier can move a greater volume of aircraft up and down simultaneously, directly supporting a higher tempo of combat sorties. Perhaps more importantly, the 3rd elevator provides redundancy. In a combat scenario, if one elevator is disabled by enemy fire, or if one suffers a mechanical failure, the forward still retains 2 fully operational lift to maintain flight operations. If the Fujian loses 1 elevator, its ability to cycle its air wing is much reduced. Furthermore, the physical positioning of the elevators reveals subtle but important constraints. On the Fujian, the forward starboard elevator is positioned in a suboptimal location. It is positioned directly adjacent to the ship's starboard jet blast deflector. A jet blast deflector is a heavy, water-cooled metal panel that is raised from the flight deck behind the catapult to protect crew members and parked aircraft from the searing heat and force of jet engines firing at takeoff. Because of the close proximity on the Fujian, when the starboard catapult is actively launching an aircraft and its jet blast deflector is raised, the forward elevator is effectively unusable. Any aircraft riding that elevator up from the hangar bay must wait for the catapult's launch to finish and the deflector to be lowered before they can be safely rolled onto the flight deck. This creates a bottleneck during high-intensity launch sequences. The Ford's architects carefully considered this geometry. While the Ford's two forward elevators are also positioned on the starboard side, their placement relative to the catapults and deflectors is optimized to ensure that elevator operations can proceed largely independently during catapult launches, keeping the flow of aircraft moving without pauses. Once the aircraft are on the deck and armed, they must be launched. Both the Gerald R. Ford and the Fujian utilize electromagnetic catapults, representing a technological upgrade from traditional steam catapults used since the 1950s. The American system is known as the Electromagnetic Aircraft Launch System, or EMALS. Steam catapults are heavy, require massive amounts of fresh water, demand intense mechanical maintenance, and provide a violent jolt of acceleration that puts immense stress on aircraft airframes. Electromagnetic catapults use linear induction motors to generate a magnetic field that propels aircraft down a track. This allows for a smooth and calibrated acceleration. However, pioneering this revolutionary catapult proved to be a grueling ordeal. The Ford experienced years of severe delays, cost overruns, and publicized mechanical failures as engineers struggle to bring EMALS to operational readiness. Troubleshooting complex problems and managing massive electrical pulses presented unprecedented engineering challenges. Components failed prematurely, and initial reliability rates were too low. The Americans paid a heavy price of being the first to invent the system. Conversely, the Fujian appears to have enjoyed a much smoother and faster timeline in getting its electromagnetic catapults ready to launch aircraft. The smoother progression partly reflects the distinct advantage of being a latecomer. Chinese naval architects and engineers have observed the American struggles and refined their own designs without having to stumble through the initial discovery. Furthermore, by transitioning directly from the ski jumps of the Liaoning and Shandong to the electromagnetic catapults of the Fujian, the Chinese Navy was able to skip the entire generation of steam catapults. This allowed them to focus all of their research and development funding, as well as their engineering talents, on mastering a single modern catapult system, rather than splitting resources to maintain legacy steam catapults. Despite achieving operational status, the Ford's catapult system still suffers from a significant flaw rooted in its development. The EMALS installation on the Gerald R. Ford lacks electrical isolation switches between the individual catapult tracks. In a conventional system, if one catapult breaks down, the repair crew should be able to flip a switch, isolate the power from that single broken catapult, and safely repair it, while the other catapults continue to launch aircraft. On the Ford, this is currently not possible. Because the electrical systems are intertwined without isolation mechanisms, fixing a severe fault on one catapult often requires the crew to shut down the electrical power to every single catapult on the ship. It's all or nothing. This means a localized mechanical issue can force a complete halt to all aircraft launches across the carrier until the repair is finished. It is currently unclear through open source intelligence whether Chinese engineers have integrated isolation switches into the Fujian's catapults system, or if they too suffer from this issue. To mitigate the risk, we must also look at the number of catapults. The Gerald R Ford is equipped with 4 electromagnetic catapults. 2 are located on the bow and 2 are located on the angled waist deck. The Fujian is equipped with 3 catapults, 2 on the bow and only 1 on the waist. The primary benefit of the Ford having 4 catapults is enhanced redundancy. If 1 catapult on the Ford breaks down, the ship still has 3 available catapults to maintain a rapid launch cycle. If the Fujian loses a catapult, it is down to 2, severely restricting its sortie rate. However, it is important to understand that the actual boost to the sortie generation from having a 4th catapult is unlikely to be substantial. An aircraft carrier only has a finite amount of flight deck. A flight deck team can only manage a specific number of aircraft at any given moment. The limiting factor for launching jets quickly is really the number of catapults available. The bottleneck is the time it takes to move the aircraft, fuel them, load heavy bombs onto their pylons, and taxi them to the launch position. Therefore, while the 4th catapult is a luxury of redundancy for the Americans, the 3 catapults on the Chinese carrier are generally sufficient for launching aircraft as fast as they can be armed and staged. The true measure of an aircraft carrier's firepower is the carrier airwing it carries. Here, the Fujian holds a temporary advantage. The Fujian was designed to operate China's 5th generation carrier-based stealth fighter, the Shenyang J-35. The J-35 provides the Chinese Navy with a low observable airframe equipped with advanced active electronically scanned array radars, sensor fusion, and superior situational awareness capabilities. The Fujian has already been photographed operating the J-35 in 2025. In stark contrast, the USS Gerald R. Ford was not originally designed or fully equipped to operate the American 5th generation fighter, the F-35C. The Ford currently relies exclusively on the 4th generation F-A-18E and F Super Hornet as the primary strike and air superiority fighters. The F-35C requires specialized infrastructure that was not included in the Ford's initial build. This includes the special classified spaces for mission planning, upgraded data networks for handling the massive amounts of information the stealth fighter gathers securely, and heavier thermal shielding on the flight deck to withstand the extreme heat generated by the F-35C's high-thrust engine. Extensive and costly modifications need to be completed before the Ford can deploy with stealth fighters. However, this American shortcoming is temporary. The second ship of the Ford class, the John F. Kennedy, has been built to operate the F-35C from the very beginning, remediating the design lag of the lead ship. Setting aside the integration of stealth fighters, both carriers are designed to operate highly balanced, capable, and diverse airwings tailored for modern air combat and naval combat. The Ford Strike Group utilizes an ecosystem of aircraft. The Super Hornets form the versatile backbone, conducting both long-range strike missions and fleet air defense. They are supported by the EA-18G Growler electronic warfare aircraft. The Growler jams enemy radars, blinds surface-to-air missile sites, and dominates the electromagnetic spectrum to protect the strike package. For airborne early warning and control, the Ford relies on the E-2D Hawkeye. The Hawkeye is the eyes of the fleet. Flying high above the carrier, its massive rotating radar dome can detect enemy aircraft, low-flying cruise missiles, and warships hundreds of kilometers away, acting as a flying command post to direct interceptors. Logistics, personnel transports, and anti-submarine warfare are handled by the CMV-22B Osprey tilt-rotor and the MH-60 Seahawk helicopters, respectively. The Fujian fields a remarkably similar air fleet, reflecting a clear convergence in global naval aviation doctrine. The Chinese have recognized that a carrier cannot survive with fighters alone, but also relies on support elements. The Fujian's primary strike and anti-ship platform is the catapult-capable Shenyang J-15T. This is a large, twin-engine, long-range fighter based on the Russian flanker design, with modified landing gear for catapult launches. While the J-15T carries the heavy ordnance, the stealthy J-35 will likely focus on air-to-air combat, escort duties, and piercing enemy air defenses. To match the American Hawkeye, the Fujian will deploy the KJ-600. The KJ-600 shares a visual and functional resemblance to the E-2D, featuring twin turboprop engines and a large rotating radome, providing the Chinese fleet with its own over-the-horizon radar coverage and command capabilities. Chinese rotary wing includes the Z-20 medium helicopter for utility and search and rescue, the Z-18F for hunting submarines, and the heavy Z-8 transport helicopter. When we compare the sheer volume of combat power, we must look at the number of aircraft carried on a typical deployment. The Gerald R. Ford, utilizing its immense deck space and efficient layout, carries a larger complement of aircraft. An American carrier air wing typically deploys with roughly 70 to 75 aircraft of all types. In a major wartime surge scenario, the Ford has the physical capacity to carry upwards of 90 aircraft, although this would severely cramp deck operations. The Fujian is a massive ship, but is slightly smaller in overall displacement and total flight deck compared to the Ford. The Fujian may carry a typical air wing of roughly 60 aircraft. The difference in aircraft capacity gives the American carrier an edge in the total ordnance it can deliver, the number of combat air patrols it can maintain, and its overall endurance in a sustained air campaign. To detect and defend against incoming threats, both ships have advanced sensor suites, but they utilize fundamentally different designs for their primary radar mast. The Fujian utilizes a state-of-the-art integrated radar mast. This architecture encloses the ship's various radars, most notably the active electronically scanned arrays of the Type 346B, within a clean and angled superstructure. The primary advantage of an integrated mast is stealth. By hiding the jagged antennas, cables, and devices behind flat radar-absorbent panels, the island's overall visibility is significantly reduced. This makes it much harder for missiles to disable the island and the key radar systems. Furthermore, enclosing the sensors helps manage electromagnetic interference, carefully isolating the ship's own emitters from jamming each other. The Gerald R. Ford uses a more conventional radar mast configuration. The lead ship was equipped with the dual-band radar system, which combined the AN Spy-3 X-band radar and the Spy-4 S-band radar. While this system is capable in a detection role as far as radars go, the external mounting of these large arrays creates a more complex physical profile. This increases the island's radar signature compared to the integrated mast found on the Chinese vessel. It is worth noting that future Ford-class ships are moving to the Enterprise Air surveillance radar system, which will alter the island's design. But the lead ship retains the dual band setup. We must discuss the most profound difference between these two Leviathans, their propulsion. This engineering choice dictates the utility of the vessel. The Gerald R. Ford is powered by two Bechtel A1B nuclear reactors. The advantages of nuclear propulsion for a carrier basically alter the strategic math of deployment. Primarily, the Ford has effectively unlimited range. The American carrier can steam at sustained high speeds, well in excess of 30 knots, for weeks or even months on end without ever needing to take on marine fuel. This allows an American carrier stationed in California to sprint across the Pacific Ocean to respond to a crisis in the South China Sea with unmatched strategic mobility, link up with locally based warships to form carrier strike groups, and be ready to fight. Furthermore, nuclear reactors generate an immense and highly stable supply of electrical power. This electrical grid is essential for firing the electromagnetic catapults, for powering the advanced radars, and ensuring the ship can support the high-energy weapons of the future, such as lasers. But perhaps the most crucial, yet underappreciated advantage of nuclear power is internal volume. Because the Ford does not need to carry millions of liters of fuel just to run its own engines, that massive internal space can be repurposed. The tanks that would hold ship fuel are instead filled with millions of liters of aviation fuel for the fighter jet. The empty spaces are converted into magazines to store bombs and air-to-air missiles. This immense storage capacity allows a nuclear carrier to sustain high-tempo flight operations for much longer periods before requiring resupply. The Fujian, tied to conventional steam power, must dedicate a large portion of its displacement to bunkerage for its own fuel. It cannot sprint endlessly. It will need to periodically withdraw from combat operations, slow down, and rely on a replenishment vessel to take on fresh fuel through hoses spanning the open sea. This underway replenishment process is time-consuming, complex, and leaves both the carrier and the supply ship highly vulnerable to attack by all sorts of enemies. However, any defense analyst must acknowledge a critical operational nuance when discussing nuclear propulsion. An aircraft carrier never fights alone. It is the centerpiece of a carrier strike group, surrounded by a protective screen of cruisers, destroyers, and attack submarines that provide essential overlapping layers of air defense and anti-submarine warfare capabilities. For the United States Navy, the majority of these escort ships, such as the Arleigh-Burke-class destroyers, are conventionally powered. Therefore, while the Gerald R. Ford itself never needs to refuel its engines, its escorts absolutely do. The entire carrier strike group remains tethered to the combat logistics and the vulnerable fleet oilers. The operational speed, range, and endurance of the American carrier strike group is dictated by the conventional destroyer in the formation, not the nuclear carrier at its center. If the destroyers run out of gas, the carrier must slow down or risk operating without its defensive shield. This reality somewhat mitigates the strategic mobility advantage of the nuclear supercarrier, as the fleet as a whole must still move at the pace of its logistics tail. Nevertheless, even accounting for the conventional escort, the tactical advantages of having a flagship that can independently generate endless electrical power, maneuver indefinitely, at top speed and devotes its internal volume to storing aviation fuel and munitions remain decisively in the Ford's favor. While the Fujian is a big achievement, it is not the final evolution of Chinese aircraft carriers. Satellite imagery from China's Dalian shipyard reveals that China is constructing its next-generation supercarrier, designated the Type 004. This new vessel demonstrates that Chinese naval architects have learned lessons from designing and operating the Fujian, and they are seeking to close the remaining gaps with the Ford. The Type 004 appears to be a nuclear supercarrier. Open source intelligence has identified what is likely to be a reactor containment section within its modules. Moving to nuclear propulsion provides the immense electrical generation and unlimited range that currently gives the Gerald R Ford its edge. Furthermore, recent modifications to the land-based carrier testing facility in Wuhan shows a larger overall deck layout with the island superstructure moved significantly aft, directly mirroring the layout of the Ford class. The island on the 004 is also expected to be significantly smaller than the Fujian because it will not have a smokestack. With the added power of nuclear reactors, the Type 004 is expected to feature 4 electromagnetic catapults rather than the 3 found on the Fujian. The massive nuclear-powered Type 004 is what will likely define Chinese power projection in the 21st century. Both the Gerald R Ford and the Fujian represents the pinnacle of their respective nations' naval engineering to date, although China is still progressing with the nuclear-powered Type 004. The Ford is the ultimate refinement of nearly a century of American experience in carrier operations. It pushes the boundaries through immense nuclear power, automation, and a robust flight deck layout. It has suffered the growing pains of pioneering the electromagnetic catapult, but it stands today as possibly the most complex warship ever constructed. The Fujian is a testament to China's rapid industrial, technological, and military ascent. By skipping entire generations of legacy steam catapults, the Chinese shipbuilding industry has fielded a highly capable carrier that directly challenges American naval power in the Western Pacific. While the Fujian is constrained by its conventional propulsion and less optimized flight deck layout, its integration of electromagnetic catapults and a modern, stealth-capable airwing make it a formidable supercarrier.